Okay, in this definition of the current density, N is the number density of charges of current carriers. Whereas Q is the charge of the current carriers. In the example of a metal, this N is just how many electrons that are free to move per unit volume. This is what I call the N. And Q is the charge of an electron, 1.6 times 10 to the power minus 19 coulombs. And Vd is the drift velocity. Now, another thing that you need to pay attention to is that at least currently, we are only discussing what we call the direct current. A battery creates this direct current in the sense that when you connect a battery to a circuit with some resistor and capacitor, the current will flow only in one direction. It doesn't change its direction. That is what we call a direct current. And that's the kind of current we will be studying for at least next week also. And after that, we will, of course, also consider what happens when the current is changing directions. For example, the city electricity, it is not direct current, what it's called an alternating current, because it just changes its direction like 50 times per second. But for the time being, we are just restricting our attention to direct current. Now, any other questions on these things, the current density, the resistivity, etc.? Now, this will be one of the most important expressions for us. Now, before going that, let's look again back at this expression. So, does this rho depend on the electric field? What would you expect? Well, let's see. The mass of an electron, will it depend on the electric field? No. The density of, number density of the electrons, will it depend on the electric field? No. The charge of an electron, will it depend on the electric field? Yes? Charge of an electron. It's always 1.6 times 10 to the power minus 19 coulombs. Now let's come to this tau, the average time between two collisions. Will it depend on the electric field? Well, how will it depend on the electric field? Why should it depend on the electric field? You said yes, but why should it depend on the electric field?
Because electrons move faster and this creates more collision.
So electrons are moving faster, so it will be colliding with the next atom earlier. Well, let's see. Well, there are two things that you have to keep in mind. One is the actual velocity, actual speed of the electron is quite high. It's like 10 to the power 6 meters per second. Now, the external electric field will cause the electron to gain a speed like 10 to the power minus 6 meters per second. So it's like the change in the velocity of the electron due to the electric field is like 1 part in 10 to the power 10. So that will not really change the collision time. Another thing to keep in mind is that if the electric field causes an electron to move, to accelerate in this direction, if there is this electric field. So as the electron is moving in this direction, it will be slowing down. Now it will be moving faster. Its speed will get larger because of the acceleration. So it will collide with this atom earlier. But as it's moving from here to here, well, the electric field will cause the speed of the electron to get smaller. So the time it takes for the electron to move from here to here will be larger. The average, well, it will not really change much. Of course, there will be some dependence on the electric field of tau. But for reasonable electric field, that's for small electric fields that do not create a huge drift velocity, that change will be negligible. So we can say that this is correct, by the way, for metals. For metals, we can say that the resistivity should be also independent of the electric field. So when we write this expression, the resistivity over here doesn't depend on the electric field, and the fact that rho doesn't depend on the electric field is what we call the Ohm's law. Rho is a constant that doesn't depend on the electric field. It's a constant in that sense. It does depend on the temperature. If you change the temperature, it will also change, but it doesn't depend on the electric field. That is the crucial thing. Now, if you imagine this metal, and let's just assume that the electric field is uniform across it, and let's say this metal has a cross-sectional area A and a length D. Now the potential difference across these 2 points, this delta V, will be equal to E times D. So the potential difference is nothing but the product of the electric field times the distance, if the electric field is uniform. Well, we also know that the electric field is nothing but the resistivity times the current density times D. Well, I'm not writing the vectorially. The current density is the current per unit area. So the potential difference across this object, delta V, we define it as I times R, where this R is equal to rho times D over A. This is the resistance of this resistor. Now, if you look at the resistivity, well, the mass of the electron is the same. The electric charge of the electron is always the same. Well, the density of the electrons, it depends on material. And the tau, the average time between 2 collisions, also depends on the material. But none of these depend on the amount of material you have. So this rho, the resistivity, is a property of the material itself, not about the size or the shape of the material. But if you look at the resistance, resistance is the product of resistivity, which is a property of the material, multiplied by some factor that depends on the shape of the material. So if from the same material you make objects of different sizes, of different geometries, the resistance will be different. So the resistance is the property of a particular object. Resistivity is a property of the material. Now, of course, this is the expression for the resistance of a resistor in which the electric field is uniform. It's like a cylindrical shape, a right cylinder with some well-defined area and some well-defined distance. For an arbitrary electric field, for example, you can create a resistor which has a cylindrical shape, and you send the current from the inner cylinder towards the outer cylinder. the expression will be different. Even in this example, if you imagine this as a cube, the resistance in this direction will be different than the resistance for current running in this direction. So that's also something you have to pay attention to. The resistance also depends on in which direction you are trying to make the current flow. Now, an easy way to calculate the resistance of, let's say, arbitrary objects, for example, you can imagine an object of this shape. Now, this doesn't look like the previous shape that we studied, like this one, so we cannot use the same expression. But what we can actually do is just imagine that this is made up of very thin objects. Now, each one of those, let's take this one. It does look like this object. It's just, if this is a part of a cone, this is just a disk, almost right cylinder. Almost. There's a slight difference, but that difference you can just ignore, or it will be negligible if you take this even smaller and smaller. So you can imagine this object the same thing as one of them connected in series with the other one, connected in series with the other one, connected in series with the last one. So we have many resistors. We have this object of irregular shape. We divide this into very small objects which has regular shapes like this one. Since each one of those very small parts is a regular object, each one is a regular object, so we can use this expression. Since we can use this expression for each one, we know the resistance of each one. And then we can just sum them up to obtain the total resistance of this thing. Let's actually do it. Let's do an example. Suppose we have a cone and a resistor in the shape of a cone almost. So this is a cone with the tip removed. Here we have the thickness R1, the radius R1. On the other side we have the radius R2. And we would like to calculate the resistance of this thing. Now we can just start by looking at, let's say, dividing this into thin disks. And let's also imagine that this whole thing has a height h. Let's just pick one of them, this one, over here. At a distance, let's say x. Let me take this as our 0. This distance is x0. This one over here is x. And the whole thing is x1. Eventually, I will relate everything to R1, R2, and H. But just for the time being, it will just simplify some of the calculations that from this tip, which doesn't, I mean, this is just a mathematical point, the piece that the top of our resistor, the beginning of our resistor, let's say, is at a distance x0. Then we are considering an arbitrary disk over here, which is at a distance x, and that arbitrary disk has a thickness dx. It has a thickness dx. It is at a distance x from that point, and this part is at a distance x1 from that point over there. Now, the resistance of this very small thing, very small disk, let's call it dr. If you remember the expression of the resistance of a cylinder like this, it is the resistivity of the material multiplied by d is the thickness of the resistor, and A is the cross section. It's rho. Well, the thickness is dx. Now we need to calculate the cross section. Let's just say this radius is r, dx over pi r squared. Now the problem is, the next thing we have to address is, of course, this r depends on x. So if we change x, if we take this disk, we will have a different r. But let's consider these triangles. So this is my r. This is the point P. At a distance x0, the radius is r1. At a distance x, the radius is r. Do you agree with this picture? So I'm just considering, okay, this is my radius. Here there is this triangle. I just copy it over here. This is the length r. This is this radius over here, which is r1. r1 is at a distance x0 from this point P. And r is at a distance x from the point P. But this triangle also tells me that r1 over r should be equal to x0 over x. No, x is the total distance from P. So, I mean, you can just also say that the tangent of this angle is r1 over x0 or r over x. They are both equal to the tangent of this angle over here because we are considering right triangles. So this already tells me that r is equal to x times r1 over x0. This is how this r over here depends on x. So the resistance of that very small disk is just rho times dx over pi r1 squared over x0 squared times x squared, or let's say rho x0 squared over pi r1 squared times dx over x squared. I just substitute this r over here. Now, of course, I divided this whole resistor into very small parts which are connected in series. And I know that the total resistance of this object is nothing but the sum of the resistances of each one of those bits. So that tells me that I have to sum these. The resistance of each one of those disks. Well, the resistance of each one of those disks, we have already evaluated it in terms of the thickness of the disk. And in the limit, when we have infinitely many disks, each one with a thickness 0, this is nothing but an integral. Rho x0 squared over pi r1 squared dx over x squared. Well, the minimum value of x, what's the minimum value of x? x0. The maximum value, x1. x0 to x1. Now, if you take this integral, this will be equal to rho times x0 squared divided by pi r1 squared times minus 1 over x from x0 to x1. R is equal to rho x0 squared divided by pi r1 squared times minus 1 over x1 plus 1 over x0. Okay, let's just check one thing. The resistance is defined to be a positive number. Is this positive? That's the first thing to check. Is this positive? Well, let's see. Remember, x1 is larger than x0. If x1 is larger than x0, 1 over x1 is smaller than 1 over x0. So this is the larger number, which is positive. So the resistance is positive. So although there is a minus sign over here, there's no problem. We know that this expression is always positive. Now, of course, this expression is not that nice in the sense that in our system, we know R1, we know R2, and we know this H. That's the only things we know. We define these things x0, x1, x0, and x1. Well, we should better express x0 and x1 in terms of the things we know. Well, we can use this expression over here. Well, let's look at this one when x is equal to x1. Well, let's look at this one. So this already tells me that R2 should be equal to, well, the R2 is the distance when x is equal to x1 times R1 over x0. Well, this is at least one expression we have. So this tells me that x1 over x0 is equal to R2 over R1. And furthermore, we know that x1 is nothing but x0 plus h. So we have two equations for the two unknowns. You can solve for x0 and x1. Once you solve for x0 and x1, you can substitute it over here, and you will have the resistance in terms of the geometric properties of the resistor you have. Now, any questions on this? You can basically do the same trick, whatever your system is. Just divide it into small parts whose resistances you already know. No, it wasn't negative. We didn't assume it to be positive. Resistance is defined as a positive number. It has to be positive. This is not negative. We just proved that this is a positive number because x1 is larger than x0. So this sum, minus 1 over x1 plus 1 over x0, is a positive number. This is larger than 0. We didn't assume it to be positive. It is positive. So let's say x1 can be 5 centimeters, x0 is 1 centimeter. So this is minus 1 over 5 centimeter inverse. This is plus 1 centimeter inverse. That's a positive number. You see, if you want to assign some directions to certain quantities, in the sense that this causes energy loss, energy dissipation. If you calculate the amount of energy stored in your system, let's say, it will be this will contribute a negative to that number. Or the amount of work that your battery does on the system, or let's say the amount of work that you can extract from your system, this will again contribute negatively. Because the battery gives some power, and some of that power is used up by the battery, so that's a negative. Negative in the sense that it contributes negatively to the amount of work that you can extract from a given circuit. But the resistance itself is defined as a positive number, just like the coefficient of friction. They are defined to be positive numbers. Of course, they cause losses in your system, so they are negative in that sense, but nevertheless, the coefficients themselves are defined to be positive numbers. Resistivity is a similar coefficient. In fact, it is the analog coefficient. Other questions? Okay, that we are talking about it. Let's also talk about the power dissipated. Let's just review it. Let's assume we have a resistor over here. There is a battery with the positive and negative terminals. There will be a current running through it. And the current, although it's the motion of negative charges, we can always imagine the current to be the motion of positive charges in the direction of the current. They behave, whether the current is created by positive charges moving in the direction of the current or negative charges moving in the opposite direction of the current, the consequences will be identical. So we can just imagine some charge dq, let's say, moving from one side of the resistor to the other side of the resistor in a time dt. Well, if you have negative charges moving in this direction, it's just identically, if you just consider the charges stored in both ends, whether negative charges move in this direction or positive charges move in the other direction, the charges at both ends will be, the change in the charges in both ends will be the same. So what is the potential difference across this resistor, which has a resistance R? I times R. So how much charge is flowing? How much charge flows in a time dt from a larger potential to a lower potential? D cube. That is the amount of charge that moved from a larger potential to the lower potential. So, but this is nothing but the change in the potential energy of the system. So as the current is running, the potential energy of the system has changed by this much. But you see, the system is in steady state. Nothing apparent in the system has changed. So although the change in the potential energy of this charge due to this motion of the charges is this much, nothing really had changed. Now the problem is, you see, there is the electric field, which is exerting a force on the charges, which are moving with the drift, on the average with the drift velocity. But the electric field does work on the charges. So they should gain some energy due to the electric field. They should gain some kinetic energy. But on the average, they don't. And the reason is they keep colliding. They keep colliding with the atoms. So I'm trying to accelerate in this direction, let's say, and then as I'm running there, first he pushes me back, so I'm pushed in this direction, then somebody else over here pushes me in that direction. So I just cannot gain velocity. The electrons cannot gain velocity because in each collision, I'm just losing the energy that I gain due to the electric field. Yes?
Is it also the reason why the drift velocity is constant?
On the average, it will be constant. Well, there is a drift. That's the reason why there's the concept called the drift velocity. Because otherwise, if there are no collisions, under the influence of the electric field, I will just keep accelerating in the opposite direction of the electric field. And you cannot really, the drift velocity will be nothing but my velocity.
That will be a constant velocity.
No, my drift velocity will keep on increasing because there's a force and I'm accelerating. So the electric field is doing work. On the other hand, as the electron is moving from here to here, it loses this much work, the potential energy, let's say. And this lost potential energy just goes to the atoms that I the charges have collided. So the charge, as it's moving from here to here, it is constantly colliding. It should be gaining this much kinetic energy as it moves from here to here, but it doesn't. The reason is it just transfers this much energy to the atoms. So the atoms heat up, and they turn into light, or they do some other work. And this is, let's say, the energy, the work done by the charges on the atoms or on your external, whatever is connected to your circuit as a resistor. So this is the work done by the charges as they move across the resistor. But, of course, the longer you wait, there will be more charges passing through it, there will be more work done. So what we are most of the time interested in is the power. It is the work done per unit time. So the power is, you can just say it is I times, this is also I. It's I times delta V, or I squared R, or delta V squared divided by R, whichever one is more suitable. If you just replace delta V by I times R, then you get this one. Or if you replace I by delta V over R, you get this one. So this is the power dissipated by the battery. Now let's go back here in the circuit. Okay, there is the resistor, which causes power dissipation, but there is the battery which feeds us with more power. And energy conservation just tells me that the power dissipated by the resistor should be the power equal to the power of the battery. That's energy conservation. Now what the battery does is it takes the charges from the lower potential. The negative terminal will be at a lower potential, so it takes charges from here and pumps them up to a higher potential. And the work done by the battery, how much work does the battery do if it just takes the charge dq from a lower potential to a higher potential where the potential difference is just V? V times dq. It's V or delta V times dq. Since this is the work done, since we are talking about the power, it should be delta V, the work done per unit time over dt. And this is equal to, well, let me just put V over here. V times I. So this is the power of the battery. So if there's more current running through the system, the power of the battery is larger. It provides more more energy per unit time, and the power dissipated by the battery is also larger. It just dissipates more power per unit time. Again, this is just a statement of the energy conservation in the system.
So doesn't the battery move positive charge from the minus terminal, which has lower potential energy, to the plus terminal, which is higher potential? So work that we are doing must be negative. Work that we're doing must be negative.
No, the battery is doing positive work. It's just, I mean, just imagine this one. It's just moving in the sense that this charge dq has a larger potential energy over here, which would be provided by the battery. Well, you see, you can imagine this one as, no, the battery should do positive work in the sense that, here you are losing energy. That energy should come from somewhere. Don't think them in terms of you are just moving charges from there to there. Eventually it amounts to that one, but you are just putting an object, just like this. Take this one, you are over here, you are moving it at a larger potential. You are doing positive work. Gravity is doing negative work, but you are doing positive work. Battery is doing work on your system. Now, since it will be your homework for the next week, let me give a hint on the battery, on the capacitor question. Here we have a battery. Here we had our capacitor, and we were inserting a dielectric. When it is connected to a battery, such that at this instant, the charge over here is plus Q, the charge over here is minus Q, just as if there was no battery. So the work that you, and if you just display, this is the distance x. So this is the work done, this is the work that you do. So where does it go? You see, you are holding this thing. You are just, to calculate the force, what you do is you just increase x slightly by dx, and just look at how much work you do. It should be, the work that you do should be equal to the change in the potential energy. Of the capacitor. This is what we used when there was no battery. But now, as you insert the dielectric, you see, imagine there is no you are not inserting anything, this is at rest. You connect it to a battery, the charge flows Q and minus Q, and at that instant the current would be 0. There won't be any current running anymore. If you insert this dielectric by a distance dx, will there be a current now? And which direction will they be? Why is there a current to start with? If you have, let's just, to be more precise, let's assume there's a resistor over here, which will always be. So the current stops when the potential across the battery is equal to the potential across your capacitor. So that's when the current stops. Now forget about this battery for the time being. There is a charges over here. There is a potential difference across. So you insert it slightly more. What happens to this potential difference? We just discussed at the beginning of the last lecture. The potential remains the same. The potential difference decreases. So if you insert this dielectric a bit further, the potential difference decreases. But that means when you put the battery, the potential difference here is smaller than here, so there will be a more current running. If there is more current running, you see the potential energy of the capacitor will change due to two factors. One is the work that you do by inserting it, plus the work that the battery does. So these two will add up to give you the change in the potential energy of the capacitor. Now, before, when we were analyzing this problem, we had ignored this part. Without this part, we had two different results, which should be the same. Now, of course, in the homework, I still expect you to show that if you include this part, the work done by the battery, in that case, everything will be fine. So that will be still part of your homework. Okay, any questions? Any last-minute questions? Okay, there's still enough time for a quiz. You don't need to pack up.
You said you won't give a quiz on Wednesday. You specifically said half of the students can't come on Wednesday, so you will never give a quiz on Wednesday.
No, I did not say that.
Yes, you did say that. Yes, you did.
Professor said that if the students are not, then they're not going to take a 0, right?
Yeah, they are exempt from the quizzes. I have their sound recordings, remember? We can check that. Electrons are, the average speed of the electron is not changing. You see, why? Because of the collisions. I mean, if the electrons are, let's say, the electric field is in that direction. At some time, an electron can be moving in that direction, then it is decelerating. At some other instant, after some collision, it will be moving in this direction, then it will be accelerating. On the average, the speed of the electron doesn't change even in the presence of the electric field.
Waiting long only increases the temperature. Waiting long only increases the temperature.
Yes. Okay, now we have a conductor. These are what we described. Semiconductor and superconductor. Okay, superconductors are weird objects in the sense that their resistivity is 0. Exactly equal to 0. There is no resistance. If you start a current in a superconductor, it will keep going indefinitely. As far as I know, there is one superconductor which keeps carrying the same current for the last, I think, 10 years. Of course, it doesn't mean that, okay, so great, so we can store energy without any loss. But the problem is, the superconductors are superconducting at very low temperatures. The highest temperature superconductor we have currently, it should be something it is superconductor at something around minus 100 Celsius. So you have to keep them at minus 100 Celsius. Otherwise, they stop being superconductor. But keeping something at such a low temperature requires huge amounts of energy. So it's still not a lossless way to store energy, but nevertheless, we do have a superconductor which is carrying this current for the last 10 years. And there's no reduction in the current as far as we can measure. Well, the superconductors are weird. When you start the current, you are creating a drift velocity. There is a drift velocity. There is a current density. You say the drift velocity, you can also calculate it. You say this is the expression. You can treat this as a way of measuring the drift velocity. For a given system, you typically know what the number density of the charge carriers are. You know the charges of the charge carriers. And this is something you know. By measuring the current, you can determine what the current density is, so you can determine what the drift speed is. So there is a current density running in a superconductor, so there is a drift velocity in the superconductor. Not really. I mean, a drift velocity that is going too high needs a large current density. A large current density would mean you are carrying a huge amounts of current. So if you are not carrying a huge amount of current, then the drift velocity is not huge. Whether it's a superconductor, a normal conductor, or semiconductor, this doesn't change. So the drift velocity depends on the properties of the material, like the charge density and the charges of the current carriers, and the current running through it. These are typically constant whether it's a superconductor or not. So the only thing that changes is if you want to create a huge drift velocity, you have to create a huge current.
Hocam mesela bu çizdiğimiz skeçlerde tablomuz aslında süper iletkenmişçesine mi davranıyoruz?
Okay, in the sketches that we draw, we will be studying circuits in more detail later on. For example, here, my wire has a resistance. I show it over here. I assume that there is no resistance over here, because whether I have a resistor over here, another resistor over here, or a single resistor over here doesn't make any difference. So I just assume that all the resistance of my wire is over here. Now, this is the superconductor. A conductor is what we have been studying, and typically they have a large number of charge carriers. Of course, if you imagine a metal, it is made up of atoms, just a bunch of atoms, let's say. But what happens in a metal is that when you bring all these atoms together, most of the electrons will still be bound to the nuclei. They are not free to move. You see, if you imagine, I don't know, an iron atom, it has an atomic number of 76, right? It has many electrons. Most of the electrons are just cannot leave the nuclei. They will stick close to the nuclei. But there are a few, which are the most energetic electrons, that are loosely bound. Even if you just give them a small kick, they will just leave the atom and they will start moving around in the metal. So if you imagine, this is your metal. Here there is an atom which contains, this is the nuclei. There are many electrons going around it. Most of them are stuck on their nuclei, but some of them will be quite easy to be liberated. So it will just move freely. So these are what creates the current. These are the current carriers. So the current carriers in the metal is not the total number of electrons, but typically for each atom there is 1 or 2 electrons that are free to move, or almost free to move, that can be freed by a very small electric field. This is what we call the conductors. Now the semiconductors, on the other hand, N is not large. The number of carriers, the carrier density. So if you take a semiconductor in its pure form, it's an insulator, almost an insulator. N is not large, so that they cannot carry a large current, and their resistivity will be large. You see, if you remember the resistivity is inversely proportional to the density of charge carriers, current carriers. So if N is not large, then that means the resistance is small. Now, N is not large, the resistance is large. Now, the nice thing about these semiconductors, though, is that we can change their in their pure form, they are useless, these semiconductors. Whenever you hear about the semiconductor technology we have, I mean, a semiconductor is never used in its pure form. We just add some other atoms. And just imagine it like this. The electrons, they can just jump from point to point. Or you can imagine, let's look at in this classroom, and just imagine your electrons, you can just jump from one seat to the next seat. Now, if you just look at this concentration of the classroom, and if you try to jump around into empty seats, there are not many empty seats around, so you will not be able to move around much. Well, on the other hand, if you look at this region of the classroom, if I tell you that you can just leave the room now and go and see you tomorrow, these ones will be the fastest to reach the door, because there are so many empty seats and they will be able to easily jump from one seat to the other seat. Now, in the semiconductors, the number is somewhere in between. It's close to a conductor, but by just adding more seats, let's say, or removing some of the students, adding empty seats, we can significantly modify its conducting properties. That's what's nice about the semiconductor. We just add some other impurities, like, if you are following any semiconductor paper, they will be always talking about gallium arsenide, aluminum gallium arsenide, etc. These are just various impurities that you add. So you are just changing their conducting properties, and by controlling their conduction properties, we can all create these technological items, like the laptops or the projector. They are all based on the fact that we can modify the conduction properties of the semiconductors. And of course, to understand their properties, you will still need some quantum physics, some quantum mechanics. Well, that's all for at this level, let's say. Any last minute questions before you go for a break? Or, yeah, a break of, let's say, 20 hours. We will discuss that tomorrow, after you hand in your homework.